In this presentation, we will model this symmetric part under tension as only 1/4 of it, perform the simulation in 1/4, but finally we will use the mirror option in ABAQUS to view the result in full model. This part can be divided into 4 symmetric portions. You can also use only one symmetry line depending on the shape of your part. In this case, each quarter will look like this. Notice how the geometry and the load is similar in each portion. Symmetry line crosses the quarter portion along this edge and along this edge. To understand the definition of symmetry plane or symmetry edges, let's check this object in XY plane. In 3D space, this line is represented by XZ plane. Similarly, we can call a line along this edge to be YZ plane. These are two letter notation for planes. Another simple way of naming planes are by normal direction. For example, if we draw a normal to this XZ plane, it would be parallel to y-axis. So we can simply call this XZ plane to be Y plane. So calling this plane Y plane would be one letter notation to define a plane. Similarly, this plane can be called just X plane. Back to two-dimensional part. For this quarter, symmetry line crosses along this edge and this edge. So this edge and this edge. In ABAQUS, at this edge, we will use X symmetry because X-axis is perpendicular to this particular edge. And similarly, we will use Y symmetry for this at this edge. Moreover, if the pressure is 100 megapascal in full model, we'll also use or apply 100 megapascal in the quarter model. Notice that the stress is a normalized quantity, but instead if we use force, we have to scale it. For example, if 100 Newton force is applied here, we have to use 50 Newton force for the quarter model. As this edge is half of this edge, the amount of force applied is also halved. We will now model this part in ABAQUS following this given dimension. Material has Young's modulus of 206 gigapascal and Poisson's ratio of 0.3. The applied stress is 100 megapascal. Let's move to ABAQUS. First, we will draw the part in two-dimensional space with the given dimension. Notice we will only model this part. So this will consist quarter of this part. So we will get rid of these edges using trim. So next we will define the material with the Poisson's ratio of 0.3 and Young's modulus of 206 gigapascal. Make a solid section. Assign the section to this part. Make an assembly. Independent is good. Make a step, static general, accept default. The load is pressure and we will apply pressure of 100 pascal. The direction is wrong. We can just correct it by putting a minus sign in front. To understand how symmetry line works, Let's say this is the undeformed formation of this object, and since we apply load, this is gonna elongate in this direction and there would be contraction along this direction. But it's important to notice that this symmetry line doesn't move to the left or right, and this symmetry line doesn't move to the top to the bottom, either in the undeformed configuration or deformed configuration. One more observation is that this line never rotates or tilts to the left or never tilts to the right. That means this line will never have any rotation about the z-axis. So if this is x and y-axis, so we can be very sure that this line is not going to move along x-axis and this line is not going to rotate around the z-axis. Similarly, this symmetry line will not move along the y-axis, will not go top or to the bottom, and it will also not rotate around the z-axis. So to model symmetry boundary condition, we have to apply those boundary conditions, as I said, to here and here. To start with this line cannot move along x direction, and this line can also not tilt around z direction. We can define this boundary condition by giving a particular displacement and rotation. If this is x symmetry, we will define that at this edge, this line cannot move in x direction, and u1 is representative of x direction, u2 for y direction, and ur3 for rotation about the z direction. So as I said, it will not have any rotation about z direction. So putting 0 means they are not moving in these degrees of freedom. And by that, our definition of x symmetry is complete. To define the y symmetry, we'll need another boundary condition, optionally naming it, and define that this edge cannot move in y direction, which is u2, and cannot rotate around z direction, which is ur3. By that, you have defined the symmetry boundary condition that is appropriate to these two symmetry lines. There is again a shortcut to this x and y symmetry. For example, let me delete this x symmetry and give another boundary condition. So there is an option that says symmetry. So if you select that and select this edge, from this menu, you can select directly this x symmetry, and your x symmetry boundary condition has been applied. So these two ways of applying symmetry boundary condition, but then you choose which one you should use. In next step, we will define the mesh. It will be very coarse, but we accept the default and submit the job. It will take a couple of seconds to complete. And it has been completed. Here you can see the stress distribution in 1/4 of this part. We can use the mirror option to mirror this part with respect to this line, such that we have another half or another quarter to the left. Let's try to understand which plane this is. So this plane would be YZ plane. So we will go to mirror option and mirror this YZ plane. And this plane is XZ plane. We can further tick this XZ plane, apply, and here you have result for the whole part. Notice that how we have drawn this quarter of the part such that this borderline is along the y-axis and this borderline coincides along the x-axis. That's why we could use the default global x and y plane mirror to get the full part. If we did not follow this convention, after mirroring, your part could have looked totally different. For example, this quarter is here and this quarter could be ending up several meters away from this.